Welcome to the University of Tennessee Nuclear Engineering Program, Colloquium Program. My name is Lee Dodds, and it's my privilege to introduce today's speaker. But before I do that, I would like to recognize a couple of students, namely Jared Edwards, who received the Outstanding Paper Award at international meeting at the Institute of Nuclear Materials Management. He receives this nice plaque and a check for $1,000. He already has the check, but let's honor him with a round of applause. Jared, come down here. Congratulations.
Thank you, sir.
Okay.
Hi, Mom. She's watching.
Well, no, she's not watching today. We have a little technical difficulties going on over here. Let me give you a little history about our webcast. We've done, the last 5 that we've done, we have now, counting today, this is the 5th one, we have a 40% success rate. Okay, so, and we're not sure, it's a different problem every week, and Murphy's Law's got us. We got 2 backups. There's a backup video machine here, and then I got Dick with another backup video machine. So we will have an archive to put, so your mother will eventually get to see you, but not live in real time, but on the archive. Okay, let's get to today's speaker, who is Dr. William Summers. He is the program manager of the Hydrogen Technology Laboratory at the Savannah River Technology Center. Dr. Summers received his Bachelor of Science degree in Chemical Engineering from Case Western Reserve and his Master's and PhD from the University of Pittsburgh. He is, as I said, he's a program manager at Savannah River for the Hydrogen Technology Lab. He has over 30 years experience in the field of advanced energy systems, including areas of solar energy power plants, thermochemical hydrogen production, coal gasification, and hydrocarbon fuel processing, and fuel cell power plants. He has led numerous hydrogen R&D projects for the Savannah River, including the development of the world's first hybrid hydrogen electric transit bus, a fuel cell powered industrial vehicle, and an underground mining vehicle fueled by hydrogen. The subject of his presentation today is hydrogen, nuclear energy, and national security. Bill, welcome.
Thank you, Lee. It's a pleasure to be here, and I thank you for the invitation, the opportunity. I thank you for taking some time out of your day to listen to me this morning. I'm always pleased to have the opportunity to talk about hydrogen technology. It's something I really believe in, and hydrogen and nuclear technology, and that marriage, I think, is one that I think you'll see is very appropriate. I also think it's an opportunity. I love to talk to students. It's an opportunity for you to, I think, to maybe look at a different field, a different area that I find very fascinating, very challenging, and it's something that I truly believe in that could change the world. They're really going to make a difference in the way we live our lives. And somebody who holds a similar view about the importance of hydrogen technology is President George Bush. And you may have had the opportunity back in January to listen to the President's State of the Union address. It was quite a thrill to those of us that have been working in hydrogen and fuel cells for a number of years to have the President talk about our technology in the State of the Union. Those are very, very valuable minutes. Not very often that the President talks about a specific technology. Those of you that maybe can't read this, let me just read briefly the part of the President's statement. Tonight, I'm proposing $1.2 billion in research funding so that America can lead the world in developing clean, hydrogen-powered automobiles. With a new national commitment, our scientists and engineers will overcome obstacles to taking these cars from laboratory to showroom so that the first car driven by a child born today could be powered by hydrogen and pollution-free. Following this is more than just a kind of a soundbite in the State of the Union. The President has shown a real commitment to hydrogen technology, and it's really being viewed now as a presidential legacy issue, and the legacy being the president. It's not going to happen during his term in office, but he wants to start the country on that path toward energy independence and towards hydrogen. But the part of this that really kind of hit home with me was the last part where he says that the first car driven by a child born today could be powered by hydrogen and pollution-free. And it just so happened that about a month before this speech, my first grandson was born. His name's Jack. So I kind of use this, and I think the president put the time scale in a very good perspective there. We're not talking about something that's going to be 3 years out or 4 or 5 years out, although you might read that in the newspapers. But really, the idea that maybe a child born today, we're 15 years or so away from really being able to go to a showroom and buy a car. And so I've got this picture actually posted on my office door. It kind of helps inspire me and kind of put it in perspective for me that this is what we're working on, trying to make this a reality, Jack's car a reality. The lights are a little high. I'm not sure everybody can. They can see it. So can they see it okay? Maybe it's just the way I am. Okay, it's fine. Well, let me get more into the formal presentation. I'd like to spend a little more time talking about the national energy situation and hydrogen, why hydrogen is a key to our future hydrogen energy system, some of the challenges we have to making that a reality. And then I want to tie that and spend the last part of the talk, tie that to nuclear energy, because I think it's absolutely necessary that nuclear play a significant role if we're going to have a viable hydrogen future. Let me say just a few comments about where I work, the DOE Savannah River site. We're located in near Aiken, South Carolina, across the river from Augusta, Georgia, about 300 miles southeast of here. SRS is part of the Defense Nuclear Complex. Started up in 1950. We have 5 nuclear reactors there, although all the reactors are now retired. And the main activity at the site, really 2 areas now. One is nuclear waste management, cleaning up the products of 50 years of operation, and the defense materials production. We still have a very active program. Tritium has a short half-life, so tritium has to constantly be replenished and so forth. We are the primary DOE site for tritium handling and processing. And since tritium is hydrogen, and we've dealt with all the hydrogen isotopes for 50 years, it gives us an opportunity to do some kind of technology transfer and take some of that defense expertise that we've developed related to tritium and hydrogen and apply that in the hydrogen energy field. And so that's where the connection with hydrogen comes from with Savannah River. We do have, oops, I'm sorry, let me back up. Now I'm messed up. There we go. This arrow, there we go. Okay, we do have a large laboratory at the site, the Savannah River Technology Center. We are what's known as a DOE federally funded R&D center. We are in the process of upgrading that to national laboratory status, similar to Oak Ridge, but our capabilities are somewhat similar there. We've got about 750 people, mostly advanced degrees, technical, scientific staff. I threw this in here kind of at the last moment. I'm not sure if it shows up real well here with the lights, but this is a satellite view of the Savannah River site. I'm losing my arrow here. It must be on, there it is. You can see the green area in the center here. That is the Savannah River site. That's 310 square miles. It's about 20 or 30 miles across here. You can see how this stands out because it's really a very densely forested area. And I kind of threw this in here because I think this kind of shows what nuclear power can do from an environmental standpoint. I think if we had 5 nuclear reactors, so you can see where the operations are on the site are a few of these areas in the center here, a very small fraction of the overall site. It's really a national ecology center, and I think it shows that the minimal impact on the environment that a nuclear plant would have. Obviously, if we were looking at coal-fired plants here or something from a satellite, it would look a whole lot different. Let's talk about the national energy issues. I believe we have what I would describe as an energy situation. Currently, it's not an energy crisis yet, but I believe if we continue to operate the way we have operated for the last several decades, inevitably we will have another crisis in energy. The issues associated with that are well known to everyone. Fossil fuel reserves are limited or problematic. I'm really referring to oil there. There's arguably, some people say 30 years, some say 40 years, some say 50 years, but a finite amount of oil left. There are other fossil fuels, heavier fuels, coal and tar sands and oil shale, but they are problematic in terms of economics and certainly in terms of environmental issues. We all know that the petroleum supply that we do have is unstable. We currently import 55% of our oil. That's projected to go up to 2/3 of our oil will be imported within 15 years. And there's almost nothing we can do to really affect that right now. We're on that path, and it takes a long time to kind of change that whole energy economy. So we're very dependent on imported oil, getting more so, and it's a very unstable. There are also issues associated with urban air pollution. We used to think mainly about California and the smog in Los Angeles, but now it's problems in Denver, and Houston, Dallas, Atlanta, just about all our major cities. I don't know about Knoxville, but I'm sure it's a concern here as well. And then there's the global climate change, the CO2 issue, greenhouse effect. Most of the rest of the world has bought in on the Kyoto protocols, the European Union, Japan, more recently Canada and Russia. We're one of the few holdouts, and I don't think the U.S., and there are some flaws in the Kyoto Treaty, and there's a lot of scientific debate about global warming, but all that put aside, the U.S. needs to take a position on that, and we need to have a strategy to address that issue. And then finally, there's the impact on our national economy and security. We pay over $100 billion per year for imported oil. That affects our balance of trade. It affects the strength of our currency. So it's got a lot of other implications. But I think the main thing that's driving us right now in terms of looking for alternative energy is what we're going to remember tomorrow, September 11th, national security. And we really can't have national security without energy security. And so we need to find a way to take the oil card out of the deck, give us a lot more freedom in dealing with the rest of the world, and become independent. This photograph was from the first Gulf War. We know we've had another war since then, and if we don't do something about our dependence on oil, we know we're going to have more conflicts associated with oil. This just talks a little bit more about that issue. I'm having trouble getting this arrow here. Let me just, you can see the green line going up, our transportation oil use. Of course, it continues to increase. And then you can see our oil production, domestic production declining. It actually peaked sometime in the early 1960s or so and continues to decline. There's some indication there. You can see a slight bump up there, maybe around 2015 or 2020. I think somebody was assuming there that maybe they're going to get Congress to approve drilling in the Arctic Wildlife Reserve or some more offshore drilling. There's a few things we can do that might try to hold that line constant. But even with that, you can see what's happening to our oil deficit here. And it's just getting worse. And I find this next slide even more kind of sobering. And that is, it shows the, where am I going to get this arrow? Is it there somewhere? Oh, there it is. I see it. Okay. Let's look down here at the industrialized nations. We currently have about 500 million cars. And by 2050, we expect that to a little more than double. But that's not really where the big issue is. The big issue is over here with the developing countries. Currently with less than 100 million cars, going up to 2.5 billion. So you look out here by 2050. Now again, by 2050, how much oil are we going to have left because we're drawing down on the oil? But by 2050, we're going to go from about 1 billion cars to 3.5 or 4 billion cars. What's going to fuel those cars in 2050? It can't be oil. We've got to find something else. So the president has made the movement to hydrogen as a centerpiece of his national energy policy. And this was presented more than a year ago. Of course, it's being debated in Congress today concerning the long-term plan and the structure of the national energy plan. But long-term, hydrogen and fuel cells are seen as playing really a key role. So let's talk about a hydrogen economy. what do we mean about moving to a hydrogen economy? Well, I think the first thing to recognize is that hydrogen is an energy carrier, just like electricity. And I see this misrepresented in the popular press all the time when they write articles about hydrogen and fuel cells and so forth, that somehow we're just going to get energy out of water. We have to put energy in to get that hydrogen out, just like making electricity. As an energy carrier, though, hydrogen has some very distinct advantages. It allows us to use sources like nuclear power or solar energy or other renewables in order to power transportation. That's really the key here. How do we use those things? How do we make that energy portable? We can't really do it with electricity. Battery electric vehicles just haven't worked out. So how are we going to get there? And hydrogen really is the answer to that. The advantages of it, of course, it is inexhaustible as long as we have a primary energy source like nuclear or solar. It's clean. We start with water. We dissociate it into hydrogen and oxygen. When we use it, we recreate the water, so it's completely clean. And very importantly, it's universally available to every country. Every country has water, has some form of primary energy. They can produce their own energy. We won't be dependent upon a place like the Middle East for our energy. And it's interesting, having been in the hydrogen business for quite a few years, how the emphasis has changed almost decade by decade. This isn't a new idea. It's been around for a long time, but it just keeps it gets hot for a while and then gets put to the back burner again. Of course, it all started back in the 60s with NASA. Every manned space flight has used hydrogen and fuel cells as the power source, and the product from the fuel cell power, that water, is what the astronauts drink. So it gives you an idea of how clean it is. Actually, we think you're not really a true member of the club in the hydrogen fuel cell business until you've had a glass of water that's come out of the tailpipe of a hydrogen fuel cell vehicle. In the 1970s, we had the Arab oil embargo and the energy crisis. That's really when a lot of the technology, and what I find really interesting is a lot of the nuclear technology, and I'm going to talk about thermochemical hydrogen production using nuclear. Almost all that work was done in the 1970s. And starting about 1980, early 80s, it was all set aside, and we're dusting that off 20-some years later and going back and trying to pick up where we were in the 70s. In the 80s, most of the work went away, except for in California, the issue again of air pollution, the smog in Los Angeles. So they've had a very aggressive program in California. The focus then of moving to hydrogen was as a clean fuel because of air pollution. And then in the 1990s, we had Kyoto and a lot of concern about global warming. And so once again, hydrogen looked like it might be an answer for that. And then with September 11th, now the focus is on national security. But I think what's really interesting is all these other issues still apply. And if we move to a hydrogen economy, we can really address all of these issues. And just from the political front, this is a very bipartisan issue. We talked about the president's support for it. That second quote, if you can't read it there, I got light print. It's Representative Ed Markey of Massachusetts. He's one of the most liberal Democrats in the Congress, and he says finding affordable hydrogen car would be like finding a cure for cancer. The last quote is from the president of General Motors, who says that this could be the Holy Grail. So, some pretty high aspirations for a hydrogen economy. Let's just talk for a minute about fuel cells, because hydrogen and fuel cells are linked. Hydrogen's the fuel cell's the engine. And a fuel cell allows us we can put hydrogen in a regular internal combustion engine, by the way, and BMW is doing that, and some people think that may be the way that we transition over. But fuel cells give us the opportunity to use hydrogen much more efficiently and with no pollution. Fuel cells it's an old technology, really, in terms of when it was invented, 1839 by Sir William Grove in London, and really used, the first time practical use was by NASA. It's basically, a fuel cell is a hydrogen oxygen battery, if you will. A conventional primary or secondary cell, the chemicals are part of the battery, and as you operate the battery, you consume the chemicals in the electrodes. In a fuel cell, you feed hydrogen and air or oxygen to the fuel cell. It electrochemically reacts and produces water. And as long as you provide the fuel and air, just like an engine, it will continue to run. So it can never be discharged. Because it's electrochemical and not a heat engine, it is much more efficient than an internal combustion engine, maybe 2 or 3 times as efficient. And because there's no combustion, there's no nitrous oxide or other pollutants that are formed from it. So for those of you who are interested more in the chemistry is actually pretty simple. This is a diagram of a proton exchange membrane fuel cell. That's the most developed fuel cell for automotive applications. The electrolyte there is a perfluorosulfonic acid membrane, solid polymer membrane. Looks like a sheet of saran wrap or plastic food wrap, and with carbon electrodes on either side. And on one side we dissociate and ionize of hydrogen, and then on the other side the protons and electrons recombine with oxygen to form water. So that's the basic operation of a fuel cell. The President, prior to the announcement last January of this increased fuel program to do research on hydrogen fuel, had announced a previous program called Freedom Car, which is a partnership with the 3 major domestic automotive manufacturers and the government to develop fuel cell cars. So there's kind of 2 dual programs, one with the car companies to develop cars, and this other hydrogen fuel program mainly with the oil companies and with the research laboratories to develop technologies for hydrogen supply. And again, as the President said in his speech, the timing on this, the goal is to enable a commercialization decision by 2015 so that these cars could be in the showroom by 2020. And I say cars, and the biggest impact we can have on our economy and our dependence on foreign oil is automotive applications. But fuel cells and hydrogen are also being developed for distributed power applications as well, stationary power, portable power, even power for things like laptops and so forth. So a lot of different applications, but the main focus of the government's program is on development of fuel cell hydrogen cars. And virtually every car company in the world is developing a hydrogen fuel cell car. Most everyone's already built one, so there are prototypes out there, there are small fleets out there. And again, so some people and even some car companies saying we're targeting 2006 or 2007, or we're going to be selling these cars and so forth. But don't believe it. I mean, it may be for small fleets, special applications, but not as a consumer product for probably at least 15 years. I find it very interesting that the most creative and innovative company in fuel cell vehicles is General Motors. Most of us wouldn't expect General Motors to be out there being the leader in creativity and innovation and so forth, but they really are. And this is a very unique concept they have. You can see on the right there, they have what they call their skateboard chassis. And that is that chassis, everything in this car is electric. It's drive by wire, steer by wire, brake by wire, power by wire. Everything's by wire. You kind of run it with a little joystick, like if you were driving it on your computer playing a video game or something. Everything is contained. The entire power system and all the mechanical portions are contained inside that little skateboard there, which I think their goal is to have that 9 inches thick or so. And then they just put the body on top of it, and they can electrically adjust the suspension and so forth. So ultimately the dream here is that, you know, initially you could have a little compact car there, and as your family grew, you could change it to a minivan, and eventually you could, you know, make it a sports sedan or something, whatever, and you could just continue to have this same chassis. So it's really out of the box type thinking. What it really shows you is that when you go to something completely different and you try to break the chains of trying to be locked into the past, and we don't now have drive trains, we don't have all of the restrictions you have in a conventional car, there's some really innovative things you can do. Well, you know, all that's great, and I think that's where we're going, but there are some very significant challenges, and this is why it's going to take us at least 15 years to get there. And I really break this down into 3 areas. The fuel cells themselves are pretty much developed from a technical standpoint. Again, NASA's been using fuel cells since the 1960s. The fuel cells work fine, the efficiency's fine. most of the performance, even the size and weight of the fuel cell system, has come down to be about the same as a conventional engine. So we're almost there from a technical standpoint. The problem is cost. They cost about 10 to 50 times more than they need to, than the goal is. So we got to reduce the cost and develop mass production. And it looks like a really big challenge, but when I look at a conventional automotive engine, and if I had to estimate how much it would cost to build an engine like that, it would be a lot more than what we really pay for it. And that's kind of the magic of mass production and what the automobile industry can do. So they're kind of putting that expertise into fuel cells and driving the cost down. There are some issues as far as increasing the lifetime and durability, but again, technically I think it's there. It's mainly cost reduction. In the area of hydrogen storage, it's a different issue. Hydrogen is a great fuel, but it's also the lightest gas. And so it's very difficult to store hydrogen in a compact manner and in a lightweight manner. And that technology to fit inside that little skateboard chassis doesn't exist. And so there's a major effort underway. As a matter of fact, our laboratory, Oak Ridge National Laboratory, all the national laboratories right now are working hard on writing proposals to establish a center of excellence in hydrogen storage technology. Matter of fact, DOE is probably going to establish 2 or 3 centers of excellence in a couple different areas of hydrogen storage, and they're calling it the Grand Challenge to try to solve this issue. So that's a real challenge, developing the hydrogen storage issue. And then finally, there's the issue of hydrogen infrastructure. And the first part of this, creating a national supply and delivery infrastructure, this is what people always describe as the chicken and the egg issue. That if we had millions of hydrogen cars out there, then the oil companies would build the refueling stations. But there's no way the car companies can sell millions of cars if there's no place to refuel them. So how do you get around that chicken and an egg issue? And that's a difficult one. You've got to kind of bootstrap your way up. That's one part of the infrastructure. And plus, the total estimated cost for the hydrogen infrastructure is about $1 trillion with a T. Now, that sounds like it is a big number. It's a really big number. But if you look at what's the cost of our natural gas infrastructure and our gasoline infrastructure, it's in the same thing. We're trying to recreate that infrastructure. So it's a huge task. How do you get there? How do you get the money? How do you grow that? That's a big issue. And then the other part of that, and that's where we're going to get to in just a moment, tying it to nuclear, is we need to develop low-cost, efficient hydrogen production from non-fossil energy sources. Again, the whole ideal here is to be able to move to hydrogen that's created from non-fossil sources. So we've got to develop those production sources. This is a little bit, again, kind of a little advertisement of some of the work we've done at Savannah River Site. We built, as Lee had said in the introduction, the first hybrid hydrogen electric bus. This was the first hydrogen bus that actually went into transit service and carried passengers in the United States. It was down in Augusta. We've also done a number of kind of specialty vehicles. That's what John Deere calls their Gator vehicle, and it's a fuel cell hydrogen industrial vehicle, and then the hydrogen storage. And a couple of the more promising areas, probably the 2 most promising areas to meet that grand challenge of hydrogen storage. One is an area called complex hydrides, and that's where we store hydrogen on a powder. Rather than as a liquid or a gas, we store hydrogen chemically bonded to a powder, to a metal complex. The other option is to store hydrogen in carbon. Again, adsorbed onto carbon nanotubes or carbon structures. So we think these approaches where you have hydrogen storage on a solid are probably going to be the ultimate solution to the hydrogen storage, and we're very active in that research. Currently, hydrogen is a big business, but it's almost completely unknown. It's not a consumer business, and people don't realize how much energy goes into hydrogen today. Worldwide, 50 million tons per year of hydrogen. It's mostly for refineries and for fertilizer plants. That is, refineries that we use hydrogen to take the sulfur out of crude oil and also to make lighter products. And in fertilizer, that's producing ammonia. So you need hydrogen to produce ammonia. Currently, worldwide, to put this number in perspective, that's 200 gigawatts of energy. Now, if you consider one nuclear power plant is 1 gigawatt, That's the equivalent output of 200 nuclear power plants. That's how much hydrogen is being produced today. In the United States, it's 5% of all of our natural gas used to produce hydrogen, and 1% of our primary energy goes into hydrogen production. And projections are, because of the growth in the petroleum industry, primarily because of the need to use heavier and more sour crudes, that energy for hydrogen production will actually surpass our energy being produced by our current fleet of nuclear power plants within the next 10 years. So it's already a big business, and that doesn't count any of this hydrogen cars and hydrogen economy stuff I'm talking about. So we have something to build on, but unfortunately, all of this is based on using natural gas. So we already know how to handle hydrogen and so forth, but we got to produce hydrogen not from natural gas, but from nuclear or from solar or biomass or some other. People are also looking at those. But for large-scale use, my opinion, and I think the opinion of most experts, is that the amount of hydrogen we can produce from solar and wind and biomass and so forth is never going to be more than 5, 10, 15% at the outside. So we need something else to replace crude oil. This is a nice kind of schematic. Actually, I borrowed this from Charles Forsberg of Oak Ridge. I think it does a nice job of depicting the nuclear hydrogen future. What we're talking about is having, I keep having trouble seeing where my arrow is. Anyway, my eyes are bad. Anyway, we're talking about a centralized nuclear reactor in conjunction with a chemical plant, a hydrogen production plant, producing large amounts of hydrogen in a centralized location, and then distributing that hydrogen probably through a pipeline system to initially to, that says oil refineries, but to the current big industrial hydrogen users, ammonia plants, oil refineries, and so forth. And then down at the bottom, that's the hydrogen future. So as these hydrogen cars and hydrogen power generators and so forth come online, then we'll have hydrogen available for those. And somewhere in between, we may or may not need some type of storage system to levelize the load here. There are three basic approaches to use nuclear power to make hydrogen. One is simply, we can do it today, and actually it's already done today in some sense, since all of our electricity kind of gets mixed together on the grid, and that is we use water electrolysis. The problem with that is that electrolyzers, conventional low-temperature electrolyzers, are relatively expensive, and the overall efficiency of going first from nuclear heat to electricity and then through electrolysis is going to be relatively low. About maybe 25% efficient overall if we use conventional power plants. If we went to high efficiency next generation nuclear plants that could maybe make electricity at close to 50% efficiency, then maybe we could get the overall efficiency up to about 40% or so. The second option, and this is the option we think has probably the greatest promise, is called thermochemical water splitting. That is, we use water and we use not electricity, but we use heat and a series of reversible chemical reactions or cyclic chemical reactions to dissociate the water into hydrogen and oxygen. There we think we can get efficiencies exceeding 50%. And plus it's a big chemical plant. We think that we can get the economics reasonable, following kind of typical chemical engineering type approaches. The third approach is kind of somewhere in between those two, and that's where we use both heat and electricity, and we electrolyze not water but steam at high temperature, and the efficiency there is somewhere in between as well. And so all of these are being looked at. Thermochemical hydrogen production, again, this is the use of high temperature heat. We could, of course, just heat water all the way up to 5,000 degrees or so, and it would dissociate into hydrogen and oxygen. But first of all, we don't want to go to 5,000 degrees, and secondly, we'd have to figure out how we could keep it separated and cool it back down again. So that's not really viable. What we can do, though, is run a series of chemical reactions where we react water with some chemicals, we run another couple chemical reactions, we liberate oxygen, we liberate hydrogen, we regenerate the chemicals, and we start the loop all over again. And that's what thermochemical hydrogen production is all about. It was extensively studied in the 1970s. Typically, we need heat in the range of 800 to 900 degrees C. So we need Gen 4 type reactor heats. So we're not talking about being able to use any of the conventional light water reactors, but new Generation 4 reactors are right in this ballpark. This technology is in the laboratory scale stage. Again, it was demonstrated at the technical feasibility back in the 1970s, but we're still in the lab stage. So we got a lot of work to do to scale up this technology and tie it to the nuclear plant. There are 3 or 4 kind of leading cycles. Probably the cycle called the sulfur iodine process is the most developed and the most studied. There's a small pilot plant of this being run by the Japanese currently, and we're building a pilot plant in this country. General Atomics in San Diego has been the primary developer of this technology in the United States. This kind of shows the technology. I know it may be hard to see on there, but the reactions we have there, the middle reaction shows water coming in, and we react water with sulfur dioxide and iodine, and it forms sulfuric acid and hydrogen iodide. Then we take we separate those, and we take the sulfuric acid to the upper loop. That's the high temperature loop where we use the high temperature heat from the nuclear reactor, and we thermally decompose that sulfuric acid, and that produces water, regenerates our SO2, and it liberates the oxygen. So that's where the oxygen comes off. And then we recycle the SO2 and the excess water. And then in the bottom loop, we have hydrogen iodide, HI, and we thermally decompose that, and the hydrogen comes off, and the iodine is recycled. So we have these two chemical loops going on, with water coming in the middle, hydrogen and oxygen coming out the two systems. Of course, we need a high temperature reactor. The Gen 4 nuclear reactor program, the goals of that program are capital cost reduction, very high thermal efficiency, passive safety, a sustainable and proliferation resistant fuel cycle, and high temperature process heat. Meaning, I think right now they're targeting 1,000 degrees C. We probably don't need quite that high, but if we have 1,000 degrees C, probably the higher the better. But we certainly need at least 900 degrees C, so something in that range. And there are 6 Gen 4 reactors, but the most developed and the one that's getting the most attention and will, I think, without a doubt, be the reactor that will be the first reactor that will be built to produce hydrogen, will be the very high temperature gas-cooled reactor. And this is General Atomics' version of that gas reactor. They call it the modular helium reactor. It's helium cooled. 850 to 1,000 degrees is the helium outlet temperature. 850 is what they need for power generation using a gas turbine. Again, 1,000 degrees C is envisioned as the version of this reactor for hydrogen production. It uses coated particle TRISO fuel, graphite moderator. In their design, it's an annular core with prismatic blocks. There's another version of this that uses the same fuel and a fluidized bed configuration, the pebble bed reactor, a little bit smaller capacity, but essentially would do the same thing and uses the same fuel. These reactors, whether it be the pebble bed or whether it be the prism reactor that General Atomics has developed, they're modular and with passive heat decay, so that there's no chance here of ever melting the fuel. It's designed so that natural forces of conduction and radiation and so forth would prevent the fuel temperature from ever reaching the melting point. This is the version of that MHR that General Atomics has developed for power generation. They call it the GT MHR, GT for gas turbine. And so they've tied the reactor in the helium loop with a closed Brayton cycle using helium as the working fluid and 850 C as the outlet temperature. And the reactor is rated at 600 megawatts of thermal. Estimates are that this power system might be 47, 48 to 50% efficient, so it would produce close to 300 megawatts of electricity. So the hydrogen version is kind of taking that and taking out that gas turbine and instead putting in a heat exchanger, an intermediate heat exchanger. So in this underground silo, and again, I just can't see where my arrow is. Oh, there it is. Now I see it. In this underground silo, here's the reactor. And so beside it, in the power generating mode, this would be the power module here. This is replaced with an intermediate heat exchanger, and then there's a secondary helium loop. So we have a helium circulator, and so we're pumping helium through this coaxial pipeline to a chemical plant. it's a very good match, I think, in terms of the thermochemical process and the gas-cooled reactor, and you can see some of the characteristics there. There are other issues besides the development of the reactor and the development of the chemical plant itself. There are some kind of balance of plant issues or infrastructure issues, if you will. Some people have proposed, gee, why don't, since we have this problem of having peak hours and off-peak, and why don't we build a system and we'll make electricity during the day when it's a peak electrical demand, and then we'll switch over and make hydrogen at night when there's not a peak demand. At first it sounds like a reasonable approach. Our analysis seems to show that it probably doesn't make a lot of sense. There's a lot of capital investment in both the chemical plant and in the electrical plant. They run at somewhat different conditions, and we don't think it probably makes sense. You're probably going to want both of them to be base loaded as much as possible. Certainly we talked earlier about one option is just making electricity and then making hydrogen through electrolysis. So that's kind of a benchmark. If you can't exceed that, then why bother with all the rest of this? We think we can far exceed that on an economic standpoint. Certainly we can beat it on an efficiency standpoint, but that's an issue that has to be addressed. And then there is this issue of hydrogen storage, and then getting the hydrogen to the customers and integrating it with the end users. What do we do if we build a nuclear plant, we produce all this hydrogen, and there aren't a whole lot of hydrogen cars out there and so forth? How are we going to balance that thing and so forth? And so part of that, and we think the approach is we'll tie it to a big chemical plant. And we'll talk about that in just a moment. And then some of the other issues, and I think these are some interesting issues. People are concerned about water consumption and saying, gee, if we're taking all this water and making it into hydrogen, replacing all this fuel, all this oil, you're going to use up all our water. Of course, all that water is being regenerated as soon as we use it and so forth. But wherever that big nuclear plant is, there is some increased water consumption there. We don't think this is going to be a big issue. I think the cooling water is a bigger issue than the water, the processed water, but it's something that has to be addressed. There are safety issues here, and it's kind of interesting. It brings in new safety issues because now we have a nuclear plant, but we also have a chemical plant. And the chemical plant may have a lot of toxic chemicals or a lot of corrosive chemicals. We have tons and tons of iodine, for example, in this process, and sulfuric acid. So what happens if we spill all that sulfuric acid and it goes over to the reactor or something? So how far apart do you put these things, and who's going to regulate this? Does the chemical plant have to be regulated by the NRC? We hope not. So there's an issue of separation distance here. But on the other hand, we're trying to transfer very high temperature heat with this helium, and we don't want to have to pump that helium a mile over to the chemical plant. So what are those trade-offs? And so those are some interesting issues that are just being addressed now. We have made some assumptions and done some economics, and I think this is the last couple slides on the economics, and I can say that at least first blush we think it looks pretty promising. We think the efficiency looks like it's going to be around 52%. We're trying to refine those numbers. We're looking at what we call kind of a four-pack here. If we're going to build a nuclear plant, we probably wouldn't build one with just one 600 megawatt thermal reactor. We'd probably put 4 of these reactors together. So we're looking at a four-pack of these reactors. And we do the economics, and you can see the results over here. And it comes out to $36 per megawatt hour, or 3.6 cents per kilowatt hour, if that was electricity. This is based on a thermal value of the hydrogen. But it's about the same efficiency going to hydrogen or going to electricity, so it's probably a pretty good comparison. If we put that on a cost per kilogram of hydrogen, it's $1.42 per kilogram. And I know that probably doesn't mean anything to you, $1.42 per kilogram. But it will when I tell you that a kilogram of hydrogen has the same energy content as a gallon of gasoline. So now it's $1.42 per gallon of gasoline. Now again, this is untaxed, and this is right at the plant gate. But it gives you an idea we're not $10 or somewhere. So we're kind of in the ballpark here. I mean, I just filled my car up on the way over here. It's $1.75 or so. So that's got tax and other stuff associated with it, but that's not too bad. Now what we've tried to do is that, interestingly enough, at the Savannah Riverside, of course we always have our own little axe to grind here. We'd like to see this first plant built at the Savannah River site. We happen to have the largest ammonia plant in the country located in Augusta. They produce and use more hydrogen in a day, or not in a day, I think in 4 or 5 days or so, than what NASA does in a year. It's a huge plant, huge operation. Ammonia production requires huge amounts of hydrogen. And it would require us actually 2 nuclear plants to provide all the hydrogen that they use. So our ideal here is that we could build 1 nuclear plant, and we could put a pipeline, it'd be about a 15 or 20 mile pipeline over to this ammonia plant, and we could provide about half the hydrogen that they need for their ammonia production. And so we've looked at the cost of that. So we start with the $1.42 that we, I'm sorry, I didn't move on. We start with the $1.42 that we had for the cost at the plant gate, and then we add some cost in for some storage and for some pipeline cost, and we take credit for the oxygen. We're generating a lot of oxygen here, and at least early on we think that we can certainly sell that oxygen. We don't know in the future when there's hundreds of these plants out there whether or not we can really sell all that oxygen. We may have to vent it, but that's fine. Here we're taking credit for it. And so it pretty much balances our other costs. So we're at $1.39 per kilogram delivered to the chemical plant. Now how does that compare to what he's paying now? He's making hydrogen now out of natural gas. So we did a study, and we actually looked at a number of variations. This existing plant that has a sunk cost for all his capital. And then we looked at, what about a new ammonia plant? And we looked at some other variations of a hydrogen plant that would maybe be producing hydrogen for an oil refinery, and a couple other kind of smaller applications. And this is the results. That at $5, the 2 main parameters here are the cost of the natural gas and the credit, if any, for the carbon dioxide that we don't produce and the natural gas does produce. So based on $5 per million BTUs for natural gas, we estimate that we're competitive with no credit for the CO2. We're competitive in the small plant applications, but we still have a ways to go to be competitive with large ammonia plant hydrogen producer. Now, if we had a carbon tax, or if there was credits given for CO2, or if they were required to capture their CO2 and sequester it, we estimate that it would cost, there's a lot of estimates on that, this is kind of the middle of the road estimate, about $40 per ton to capture and sequester that CO2. And personally, I have questions technically whether we can really sequester CO2 in large amounts anyway, but assuming we could, it would cost, let's just say, $40 a ton. And at that cost, we're very competitive with natural gas. So I think the bottom line here, we think this is an attractive kind of early market, and that brings me to my summary. I hope I've convinced you a little bit anyway that hydrogen is the fuel of the future, that nuclear energy and hydrogen are natural partners in our future energy system, and that if we go that way, there will be significant benefits to our society, economic, environmental, and certainly national security benefits as well, and that we think we see a path to get there with industrial hydrogen. And so let me just close by asking you to kind of join me in helping make Jack's car a reality. Thank you.
Okay, we have time for questions and comments from the audience. Okay, Peter?
You talked about storage media. What sort of figure of merit do you use to compare the hydrides with the nanotubes? How do you, I haven't thought much about it. How would you compare? What's a good medium versus a bad medium? What figure of merit are you using?
The biggest challenge we have is the weight of the storage system. And so when we're looking at solid storage, it's the percent hydrogen by weight. And I showed the bus that we have. That bus has metal hydride storage on it, solid hydrogen storage. That's what we use in a lot of our defense work, our tritium processing. We use metal hydrides. It works great, but it only stores about 1.5% by weight hydrogen. That is, to store 1.5 kilograms of hydrogen, it weighs 100 kilograms. So the goal the car companies want are to get that up to around 6% by weight. And so that's kind of the figure of merit right now. Carbon, some people have presented some results saying they might be able to get 4, 5, 6. I mean, there were a few years ago people saying get 75% by weight on carbon, and that's all been pretty much disproved. But that's the primary one. What's the percent by weight?
Larry?
What about, you mentioned the liquid chemical hydrides like sodium borohydride. Have you looked at those?
Yeah, we haven't done a lot with them. We're doing some research there. We think the real difficulty there is the need for off-board processing and regeneration. So we've built this bus. We like the idea of being able to have a storage tank that operates just like a regular fuel tank, that you just pull up to the pump and you just hook up the hydrogen line and you fill it up, and you don't have to take anything off. So that's the only problem with the chemical hydrides, I feel, is you need to solve that issue of the logistics issue, if not the cost issue of regenerating.
In your money comparison, you had I may have missed it, but you had like a 49-cent or something oxygen credit. What's the basis of the oxygen credit?
That we assumed there. We estimated costs for liquefying that oxygen and storing it, and then that was and then delivering it to customers, and then use the current market price. I think it was $20 a ton or something like that for the delivered cost of oxygen.
Well, I was just wondering, from the beginning of your presentation, obviously there's an oxygen pipeline going out. What's going to happen to that oxygen? Is the current market, worldwide market for oxygen, anything like what we would be producing if we went with the hydrogen?
Not if we were producing enough hydrogen to replace a significant share of the oil. There's certainly not that kind of an oxygen market out there, so a lot of it would probably be vented. But one thing we're looking at is that, let's say there was a lot of oxygen available. Again, this is kind of thinking out of the box like General Motors with their car. I mean, you can enhance combustion processes. There are a lot of other things you could do if you had cheap oxygen. Certainly people are now doing a lot of work looking again at coal gasification processes. And a lot of those are air-blown gasifiers. Well, if you had a lot of oxygen available, you could go oxygen blown, and they'd be a lot more efficient and so forth. So there may be other markets developed if you had a lot of oxygen available, but we're not really kind of staking a lot on that in terms of the overall economics.
Okay. Bill?
You mentioned the efficiency of producing hydrogen. How do you define the efficiency?
The efficiency there was the higher heating value of the hydrogen divided by the 600 megawatts, the thermal energy input from the reactor system. And then subtracting out also all of the auxiliaries, including the primary and secondary helium circulators.
What's the difference in the efficiency of produce hydrogen and have a fuel cell compared to the efficiency if you produce electricity and you have an electric car? I kind of think
in one hand you'd be more efficient going with the electric car. If you just produce electricity, the issues are you've got to distribute all that power, so you have some losses in distribution, transmission losses. But the real thing that just kills that is that the battery technology just has not made it, and so battery-powered electric cars just don't have the operating range is the problem. I mean, the car companies are saying, and their customers are saying to them that they want a car that can go 300 miles on a fill-up. An electric car goes 50 or so. So, if you have to recharge your car every 50 miles, you can make a case, well, if you only drive 10 miles to work or something, as long as you charge it up every night or something, it still might work, but there's not much of a market for that. And the cost, and then typically with the batteries, there are disposal issues too. So it's not a clean technology like you might think. You got to get rid of that lead acid battery or whatever it is.
It seems a lot of people don't like the electric cars because they lack the power and some of these things that would seem pretty similar with a hydrogen car.
Actually, the power's not really an issue. No, power's not. If you have electric drive, at electric drive, you've got your maximum torque at zero speed. So, you've got a lot more torque. So these things really get off the line and so forth. So even with the electric cars, General Motors built what they call their EV1. And anybody that drove it said it was great. I mean, it just took off. It was, that was not an issue. The issue is operating range and cost.
Wayne?
Yeah, I drove one of the Ford hydrogen vehicles this summer in California. It was great. I mean, it had a lot.
Great.
But my question is, in a chicken and egg situation, you got a chicken and an egg here, because to get into to really create a situation where Jack's car, his first car, will actually be a hydrogen vehicle, not only do you have to change the infrastructure, which is a tremendous, probably a federal expense, but you also have to subsidize the manufacture of those vehicles for the first 5 to 10 years, probably, in order to get over that hurdle of the transition from gasoline to hydrogen. And I'm just curious whether in Bush's plan, from your perspective, is the federal government prepared to subsidize both sides of this, both the infrastructure and the automobile manufacturers who are trying to struggle with bringing the cost from $1 million down to, let's say, $50,000 in the next 10 years?
I don't think that they envision a lot of government subsidies. I mean, you're right, and maybe that's what it really takes, but I think that the government money is going in to subsidize the research, and the hope here is that they will develop a car that will be economically competitive. And again, when we look out 15 years or so, gasoline's $1.75 a gallon today. What's it going to be then? Now, I know back in the 1980s it was already $2 a gallon or something, and I thought by now it would be $5. But it's hard to predict those things. But I think the idea is to try to help develop the technology, and hopefully that the marketplace will take care of itself. But to me, a big part of that, and I showed on our economics for the chemical plant, was CO2 issues. I mean, if they require CO2 sequestration, then that ups the cost of all the competition.
Art?
Yeah, in the transportation sector, you have to sequester the hydrogen. In the transportation sector, you have to sequester the hydrogen to make it transportable, and then you have to release it to use it in, say, the fuel cell. And that affects the cost of delivery, and it also affects the efficiency of the cycle. Do you have any idea how big an effect that will be based on the 2 primary technologies you consider?
Yeah, it's very big. One of the points, I had a footnote on there, I forgot to mention it when I showed the cost of delivering that hydrogen to the chemical plant. And at the bottom it said no end of pipeline processing considered. For the chemical plant, that's fine. It comes out of the pipeline, it goes into his process. But to deliver that for the corner gas station, that's a huge issue. We've got the distribution system, not only the kind of the interstate pipeline, if you will, but you got all the local distribution, and then he's got to store the hydrogen at the service station, and then he's got to retail it out to the customer, and those add tremendously to the cost. And so that $1.30 a gallon maybe becomes $3 a gallon or something, or $4 a gallon. But one thing to remember is that the hydrogen cars are being developed to get 80 miles per gallon. So you could actually afford to pay more per gallon and still not pay more per mile.
It's also an efficiency thing, because it's a thermodynamic cycle to sequester the hydrogen, which changes its energy state, and then to release the hydrogen from whatever bonds you have there sequestering it.
Well, with that's a basic requirement of the metal hydride storage or the complex hydride storage, and that is they operate with waste heat. So that energy is released when you store it. When the hydrogen's absorbed onto the material, energy is released, that heat's released. But to get that hydrogen back out, you just need waste heat at less than 100 degrees C or so. So there's really no additional energy penalty.
Okay, well, our speaker will be available to answer more questions downstairs, where I think everybody knows we have refreshments. There are a few faces that I see that are new, and so we do have refreshments downstairs, and everyone is invited. But before we adjourn to our refreshments, let's express our appreciation again to Bill for his presentation. Thank you. Excellent presentation.